There are three sequencer instructions: SQO, sequencer output; SQC, sequencer compare; and SQL, sequencer load. We're going to start with the sequencer output instruction first. The easiest way to illustrate the SQO, or sequencer output instruction, is to show the same logical results with more basic or more standard logic, like you see right here. So we had you put these rungs of logic in and then execute according to the instructions. Let's go over these real quick. Input 0, we'll call that the go to next step push button. By way of a one-shot rising, executes an add instruction. And notice that the add instruction is really just incrementing N7:100. Every time rung 0 goes true, we add 1 to N7:100 and then put it back in N7:100. So you see in your logic, every time you clicked input 0 on and off, N7:100 went up by 1. We need the one shot in there because if we didn't, every time you turn on input 0, N7:100 would increment once for every program scan. We only want one increment. So N7:100 is basically the current step. Now, for the second rung, I put in the reset rung. When N7:100 increments to 4, because this is a 4-step sequencer, but remember, 4 steps is step 0, 1, 2, and 3. There is no step 4. When we increment to 4, it clears N7:100, which brings it back to 0. Okay, so rung 1 is the reset rung. Rung 2, if the current step is 0, in other words, if source A equals B, 0, then we move the bit pattern from B30 into the output word for this PLC. Now, since we only have 4 outputs, only the first 4 bits really are going to show any results with the LEDs on the PLC. If you're using a larger processor, then by all means use more bits in your bit pattern. But in the lab, I had you put in 0 for B30, 1 for B31, 2 for B32, and 3 for B33. Very simple. So when we're in step 0, it's going to put 0 into B3. B30 is going to be 0, so it's going to put nothing into output 0. In other words, no outputs will come on. When you do go to the next step switch again, then you increment N7:100 to 1, so rung 3 is true, and that moves the bit pattern of B31 into the output word. B31 should have been set to 1, so you see one LED come on. And consequently, the same behavior in rung 4 and rung 5. Now, in rung 5, to fully simulate the sequencer output instruction, when N7:100 is equal to 3, we move the bit pattern from B33 into the output word, and we turn on a bit that we're calling the done bit. Because when we get to the sequencer output instruction, we're going to have a complement of these same memory locations. Now, we're going to have a file, B30, B31, B32, B33, a file that represents the bit patterns for each step. We're going to have an integer that shows the step, and we're going to have a bit when the sequencer is done. Now, the only question that was asked in this part of the lab was what happens when you sequence once past the step where the done bit went high. In other words, when you were in step 3, rung 5, turn the done bit on. If you went one more step with the go to next step push button in rung 0, you incremented to 4, and then in rung 1, that rung is true, it clears N7:0, and then nothing is turned on. Actually, it would leave the output word in the last state, because the last thing we did was move B33 to the output word. So if we really wanted to clear everything, then we would have to clear the output word as well. Typically in a sequencer you don't do that. The outputs stay until you go to the next step. But we're just demonstrating something real simple here, so you can see logic that looks at a bit pattern of a file where it's 0, 1, 2, 3, B3, 0, 1, 2, 3, and as you sequence through those, it controls outputs. In this lab project, we've got an imaginary machine that we're going to sequence cylinders and a drill motor and conveyors. Because the MicroLogix 1000 10-point processor only has 4 outputs that we can control, we had to design it in such a way that we could group outputs together. So output 0, the first output, will control solenoid 0, and solenoid 0 controls both cylinders 1 and cylinder 2. Output 1 will control solenoid 1, which controls cylinders 4 and 5, and it will control 3M, which is the motor that drives the finished product conveyor. Output 2 will control 2M, or the drill motor. Output 3 will control solenoid 2, which controls cylinder 3. So you see there inside the blue dashed lines, we have the outputs grouped into 4 groups. Once again, we have grouped the outputs into 4 groups. Output 0 will control cylinders 1 and 2. Cylinder 1 is a stop cylinder that stops the product on the feed conveyor from running into the previous product that's actually in the workspace. Cylinder 2 pushes the current product into the workspace so the drill motor has access to it. Output 1 controls solenoid 1, which controls cylinders 4 and 5, and 3M, which is the finished product conveyor. Cylinder 4 extends the drill motor to penetrate the part that's in the workspace. Cylinder 5 is a stop that keeps the products from continuing off the end of the conveyor until the next product is pushed off behind it. So it spaces them out on the finished product conveyor. Output 2 controls the drill motor, and output 3 will control solenoid 2, which is cylinder 3. Cylinder 3, when the product has had the hole drilled in it and cylinder 2 retracts, then cylinder 3 extends and pushes it onto the finished product conveyor. Okay, step 0 in the logic that you just did a lab or two ago. For step 0 to be complete, you had several input devices that had to be in a certain state before step 0 was complete. So really, when we think of step 0, we should think of what is the machine doing when it's sitting there waiting for something to happen. Not for the next thing in a cycle to happen, but waiting to basically initiate the cycle or the sequence of functions that actually define that machine. So right now we're in step 0 and we're waiting for product. The feed conveyor is not controlled by our logic. The feed conveyor is part of a larger system, so it's a trunk conveyor that feeds a variety of products past different workstations. This is just a workstation in a series of process flow. When the correct product comes by, the barcode reader will identify it. The barcode reader, of course, doesn't read the barcode unless 2PE sees an object. So 2PE and the barcode reader are not in our control. So as product comes along, the barcode reader reads it, sees that that is product that we want to work with. Now I've paused the conveyor temporarily here just for the sake of illustration, but the next few steps that you'll see would have happened immediately. So the instant that that first product broke, the leading edge of it broke the beam from photo I0, the next step would have happened. So think of that input image that when it's true, it sets the bit that step 0 is complete. Think of that input image as not just input devices like photo I0, but it could be timers being done that you've put in there for delays. It could be any number of things, all of which have to be in a certain image. We'll call that the input image or the sequence complete image to complete step 0. So step 0 is the waiting for the first thing to happen. And the first thing that happened was the leading edge is sensed by photo I0. So we want to go to the next step. Now you have step 0 for your input image. When step 0 is complete, that bit being set to 1 is used in other logic that turns outputs on or turns them off. So in this case, output 0 energizes. Output 0 controls solenoid 0. You could even say it controls 2 solenoids if you want. We used 1 solenoid. So basically we either have common plumbing, pneumatic plumbing, running to cylinder 1 and cylinder 2, or the copper conductor that is wired to output 0 energizes 2 solenoids, and those 2 solenoids effectively send cylinder 1 and cylinder 2 forward. Now the reason we want to send cylinder 1 forward is because we want to stop any product right behind the one that we're going to work on. Now, we want to stop the next product and hold it there, and it's sliding on the conveyor. The conveyor is still running. At the same time, we want to extend cylinder 2 to push that particular product off into the workstation, into the work area, and it clamps it against a fixture that will be used to drill a hole. So at this point, okay, so we've now exerted control over the system. We went from watching an input image, and when step 0 was complete, step 0 complete, through other logic, energized solenoid 0, which caused cylinder 1 and cylinder 2 to extend. Because step 0 is complete, now we're looking for step 1's input image to match up so we can say the step 1's complete. So first we exert control over our output. That should cause machine motion, and we should sense something to feed back. Now there's several ways to do this. You could use a timer and set it for 5 seconds and just assume that the cylinders have fully extended after 5 seconds. That's called time-driven logic. Very, very poor way to write logic, but it's the cheapest. Sometimes you get stuck doing things like that. Event-driven is much better. In other words, you have an actual physical device that when it's energized, that is an event that tells you that things have moved to the next position. So we started out in a way with feedback, or waiting for the sensors to complete into the right state to complete step 0. When step 0 is complete, then we exert control over the machine. You could say by moving step 0's output pattern into the output word to control the output devices. Once the output devices change state, there'll be a machine. Step 1 is complete. When the step 1 image is complete, then in step 2 it's going to wait for the feedback from the control caused by step 1 to be complete. When step 1 was complete, we used that bit to turn on 2 different outputs. Now in the slide I show output 2 in 1 instead of 1 and 2 because we want 2 to come on first. Right now output 2 is on, which controls motor 2M, the drill motor. The reason for that is we want the drill motor up to speed before we run the drill bit into the product sitting in the work fixture. And that can easily be done with a timer. Now you could have made this 2 steps. In other words, step 2 could have been waiting for the motor to come up to speed, the drill motor, through a timer, and then when the timer is complete, go to the next step, where you energize 3M and solenoid 1 so you can extend cylinder 4 and cylinder 5. However, we just made this one step. You could make it 2 steps if you like. So we delay output 1 being turned on until 2M is up to speed. Once 2M is up to speed, then we energize output 1, which extends cylinders 4 and 5. Cylinder 5 basically puts a stop out there to stop any product that was just pushed off by cylinder 3 onto the finished product conveyor. We don't want it taking off and creating a big space, a big gap. So we hold it there until later. So 3M is started, the product conveyor takes off, but we use the stop to hold it there temporarily. Cylinder 4, of course, set with very carefully with a flow control, drives the drill motor and its bit into the workpiece to complete the work on that component. So our control was to turn on outputs 2 and 1, output 1 being delayed by a timer, and then the feedback would be cylinder 4 extending until the proc switch is made. Okay, at this point we basically have extended everything and reached kind of the pinnacle in our cycle. The product has been clamped, the product has been drilled, and any finished product is blocked by the extended stop number 2. Now we're just waiting to rinse the finished product out. In steps 3 and 4, all outputs are set to 0. However, output 2 is delayed until the tooling clears the product. In other words, we can't extend cylinder 3 until the drill motor has pulled the bit out of the part. So turning off output 1 has to be delayed until cylinder 4 is retracted. So basically we turned on output 2, then output 1, and then we turn off output 2, then output 1. So we need to delay the next step until the drill bit has been pulled out of the product. And then in step 5, we energize cylinder 3. That extends and pushes the, we'll call it the finished product, onto the finished product conveyor. Now if there was a product being held by the stop 2, it has already started to move down the finished product conveyor, and as soon as we push this off, this part will also move on down the finish conveyor. So control was to extend cylinder 3, feedback by way of proximity switch 2. That completed step 5. Now we're into step 6. Step 6, or you could say 6 and then back to 0, because we're moving away product. The finished conveyor is stopped, so that product, the one that's designated as finished because it has a blue color to it, that is actually sitting there, and we're going from step 6 back to step 0. But now step 1 is because photo eye 0 just saw product. So we're right back to the same cycle again of we sense product at photo eye 0. Now we're going to extend 2 and see, energize motor 2M, drill motor's energized. When it's up to speed, then we extend cylinder 4, cylinder 5, and the finished product that was already on the conveyor is going to be stopped by cylinder 5. See, we're into step 2. So this is something we didn't see the first time around, simply because there were no parts in the system. So once we start cycling parts through the system, there will be a finished part sitting on the finished product conveyor waiting for the conveyor to be turned on, move it to the stop. Now the reason we do that is because we don't want large gaps between the finished product going down the conveyor. Control and feedback. If you like, you could call this form a sequence planning chart. It's reminiscent of the old days when they actually included a blank form in the back of the manual that you could photocopy and then write in a description for the step and include the bit pattern. Most of these processes, though, were very large, and the addressing that shows the 4 outputs, that would have been 16 bits wide, and you would use multiple sheets for each step, because the input image may have included more than 16 inputs, most likely closer to 40 inputs. So it would have been 3 words. 48 bits is what it would take, 3 16-bit words, to accommodate an input image greater than 32 bits. So here we have kind of a blank form, and in the lab I had you write in the description and what you thought the bit patterns would be for the output. So in other words, for step 0, and by the way, there's 2 different ways you can do this. We're talking about the input image steps, step 0, step 1, step 2, step 3, etc. Here we're showing the output image. In other words, in step 0, what outputs do we want on, what outputs do we want off, and then we have a description. Step 1, same thing. So we'll throw in step 0. In step 0, we want all the outputs de-energized, all actuators in the home position. Then for step 1 output image, we want to extend cylinder 1 and 2. Remember, we did that off of output 0 for solenoid 1. That's to stop product feed and clamp the product. For step 2 for the output image, we still have on output 0. We don't turn that off because we need those 2 cylinders to stay extended. But in addition, we energize 2M, and we energize or we extend cylinders 3 and 4. Now, one thing I didn't mention there in the output image, we're turning on outputs 1 and 2, but remember, we turned on 2 first. In the logic, it's 1 step, but in the actual rung that controls the outputs, we throw in a timer and give a partial second or a whole second delay before we actually extend cylinders 3 and 4, because we want to allow the drill motor to get up to speed. So in the next step, basically all we're doing is we're turning off output 1, but we still leave on output 0 and 2. That's to retract cylinders 3 and 4, and then we delay de-energizing 3M. Mainly because we want to pull the drill bit out of the part with the drill bit turning. If you've ever drilled anything by hand, you might pull the bit out without its turning, you might not. You could almost say it kind of cuts its way out. Okay, then in the next step, we want to retract cylinders 1 and 2 and de-energize 2M. Now, I'm not trying to present a perfect sequence here. I cut it as close as I could without getting too convoluted, too complicated. If yours doesn't work out exactly the same way, as long as you understand the process, that's all that matters. I can see a lot of ways to improve this sequence, but once I developed the lab manuals, once I created the animation, going back and playing around with the sequence to tweak a little bit just didn't make any sense. All we're after here is for you to get the idea of how to plan and program a sequence. And then, of course, extend cylinder 3. Retract cylinder 3. And we're back. Remember, cylinder 3 pushed the part out of the work area and onto the finished conveyor. Okay, now taking a closer look at this. So you went through, you put in your bit pattern, and you wrote a description. Then you needed to transfer the bit pattern for output 0, 1, 2, and 3 into bits 0, 1, 2, and 3 of the first word of the file for your sequencer. So you're going to take, for step 0, you're going to take bit 0, whatever the state is on your little chart, and you're going to move it into bit 0 of B30. In this case, 0 is 0. Then you're going to do the same thing for output 1. You're going to put that in bit 1. So basically, you're building an image in B30. B30 represents the output image for step 0. So you're going to copy those 4 bits. Now I realize on the chart, you're going 0, 1, 2, 3 left to right, whereas when you're entering the values in the data table file B3 pop-up here, you're going from right to left. That's just the way it is. In English, we read from left to right, but when you're looking at values in a register, it's always displayed the other way, from right to left. And you would do the same thing for bit 2 and bit 3. So you would take the bit pattern for step 0 for the outputs, for those 4 bits up there, and you would transfer them into the first 4 bits of B30. Then we would go to step 1 and transfer those bit patterns into B31, 1 bit at a time, bit 0 to bit 0, or I should say output word bit 0 to B31 bit 0. And then the second bit for your output word goes into the second bit of B31, which represents step 1. Now the reason for using these memory locations that are numerically addressed this way, it's always good if you can use word 0 for step 0, etc. That way when you want to go look for output image for step 2, you just go to word 2. Same thing with step 2. Transfer the bits. Okay, once you executed all of this and you ran it, if you were keeping an eye on the 4 LEDs on your demo, now if you've used the MicroLogix 10-point brick, the smallest that they make, you have 4 LEDs marked 0, 1, 2, and 3. This is what you should have seen in the way of LEDs illuminated for steps 0, 1, 2, 3, 4, and 5 for the 6 steps. You may have had more steps. You might have even had less steps. I don't know. But this is what you should have seen or close to it. Once your logic is working correctly, then we had you cut the logic out of ladder 2 and paste it into ladder 6. And then without doing anything else, we had you save, download, and go online. And then we ask you this question: does your logic function the same as it did before you moved it into ladder 6? And of course the answer is no, because you have no way to execute ladder 6. Ladder 2 is the only ladder file in the program. It's the only program file, if you want. Only ladder file that executes automatically, or it's basically a continuous task. In the newer products, they refer to it as a continuous task. Ladder 3 through ladder whatever this processor allows, this particular one has a fixed number of ladder files. They're already declared for you. You can't even go create them. Whereas in the larger processors, you can create even as many as 3 through 255. So you can create a lot more ladder files. But ladder 2 is the only one that runs automatically. If you have a ladder 6, ladder something else, you have to have a JSR, jump to subroutine, instruction that jumps to that file number. Okay, so we had you add that, run to ladder 2, save, download, and go online, making sure then that you toggled B3290 on because we want this JSR to execute. Then we had you toggle input 0 on and off several times. Does your logic function the same as it did before you moved it from ladder 2 to ladder 6? Yes. Okay, then we had you copy the above rung from ladder 2 and paste it into ladder 14. So now it exists in 2 places. It's still in ladder 2 because you copied it, not cut it. You copied it from 2 and put it in 14, changed the memory address for the one in ladder 14 to B3291. It really doesn't make any difference. If you had left it B3290, it would still work. It's just that this way it gives you the ability to disable the JSRs individually instead of collectively. So go back to the rung that you copied in ladder 2, however, though, and change the JSR to file number 14. Save, download, and go online and test your logic. Be sure that B3290 and 1 are both on. And again, we ask you, does your logic function the same as it did before you moved it to ladder 6? Yes. What you're doing now is, in ladder 2, you're jumping to ladder 14, and in ladder 14, you're jumping to ladder 6. And when you're done in 6, it goes back to 14. When it's done in 14, it goes back to 2. I would like to add, even though I don't show it on the screen here, but I did mention it in the lab manual. Jumping from ladder 2 to ladder 14 to ladder 6, back to 14, back to 2, this is referred to as nesting. And you are allowed to nest up to 8 levels deep unless you're using selectable time interrupt or high-speed counter routines, and then you are limited to 3 levels of nesting. I implore you to avoid nesting more than 2 deep. In other words, jump from ladder 2 into, we'll say, ladder 6, and that's your main program file. And in ladder 2 is nothing but JSRs, program control. Ladder 6 might be your main program file, and then in ladder 6, maybe jumping to 7, then back to 6, jumping to 8, back to 6. But try to avoid any more than 3 levels deep. Also, in the lab manual, I showed you that they suggest, or rather they recommend, that you put a subroutine instruction at the front of the very first rung in each subroutine, and then in the very last rung, not the end rung, because that's permanent, you can't change that, but the last rung should be a return instruction. These aren't necessary, they're optional, and really they're a holdover from the PLC 5 days. Now some of the old timers will argue that you should use them. If you feel better using them, then by all means use them. Okay, so we had to add the following logic shown on the screen here into ladder 7. Now what we're going to do is we're going to compare the sequencer output instruction to the logic that you did by hand. And instead of using N70 and I think it was B330/0 for the done bit, we're actually going to use a sequencer output instruction that's going to use predefined control data type R6:0. And we're going to use a length of 6. And for the mask, I have put in 000F. Now if you remember from BCD or from hexadecimal, which is what this is, the little h there, the lowercase h, indicates that it's hexadecimal. So really 000F is 4 ones in the first position, that represents F, and then all zeros for the rest of the 16-bit word. So you've got bits 0, 1, 2, and 3 are ones, and then bits 4 and on up are zeros in the mask. So it's only going to look at the first 4 bits from the file when it's transferring them into the destination, which is output word 0. Now the reason I did that is because this manual was written primarily for the 10-point MicroLogix 1000 processor that has 6 inputs and 4 outputs. So you only have 4 outputs to work with. If you have say a 16-point, well then you could open up, if you wanted to, the second position there, so it would be 0, 0, and then you would want 3 and then F, because 3 is 1, 1. So that would give you the first 6 positions. Anyway, so we had you put this logic in. So right now you have your ladder logic, which you previously did, is in ladder 6. This is in ladder 7. And you've turned off B329.0 and B329.1. So if you execute the program, neither set of logic is going to execute. Now, we had you toggle B329.1 on, which is going to execute the JSR to subroutine 7, ladder file 7. Then we had you toggle input 0 on and off while observing the output LEDs. And comparing these to the pattern of output LEDs that you got from the logic that is now disabled in ladder 6. Did you get the same results with the single run of logic in ladder 7? Because that's all you got is rung 0 above here. That's all that's in ladder 7. Did that give you the same results as you did with all of the rungs that you have in ladder 6? It better had. Yes, it's supposed to. If it didn't, you need to go back and figure out where you made your mistake. If you have a lot of trouble, you can always go to support on the PLCprofessor.com website and go to support. It's back in the Contact Us tab, and send us an email saying that it didn't work, and we'll work with you. What can you say about the behavior of the integer that's part of the predefined data type R6:0.POS? That's a single integer. What can you say about that behavior compared to N7-100, which is what was in the ladder logic that's now in ladder 6? Now you may have had to go back and run it again, ladder 6, run it, and then run ladder 7 to do this comparison. However, they have identical behavior. They both serve as a pointer to point to what step you're in. How about R6:0.done, which is the done bit for that predefined data type, versus B330/0, which is in ladder 6? How did those two compare? Same results and purpose. They come on when the sequence is done, and they go off when you reset back. These two routines, ladder 6 and ladder 7, are basically identical logic. The difference is that at some point many years ago, instead of making you write all this logic, they gave you a single instruction that has all of that logic embedded in it. In the newer products, they have user-defined data types, and they have what they call add-on logic, where you can actually create your own instructions and put your logic in there and make it a single instruction, just like they've done here.